Bismillah ar-Rahman ar-Rahim. This is a steel structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 16th, 2020. Today, inshallah, we're going to continue with the flexure beam, and we will teach you how to check the shear. Usually, guys, shear is not a big deal or it's not a problem for beams. So for that, the usual practice is to design the beam for flexure strength and then check the shear and the deflection. يعني في البيمز الجنرال براكتس انك تصمم البيم على الفلكسر strength which is the moment بعد هيك تشيك الشير if it's okay or not with deflection. طبعا انتوا بتعرفوا in the beams all the time, if you make an imaginary section here, the main force is here, shear and moment, okay? So it's different from the columns. So before going further, let's first, let's say, make a quick review for the basic concepts from the mechanics of materials or strength of materials, as you would like to call it, about the shear. So if you see here, this beam, figure 5.17, okay? So in this beam, guys, so this is a beam, it's a simply supported beam, and you see here, it's a pin here and a roller here. So this is fixed or simply supported beam, okay? And if you see, this is the neutral axis of the beam. Okay, and it's loaded with some loads. Let's say we have here, or at a distance x from the left here, we take an element here, a material element, okay? And notice it's at the neutral axis. What does it mean? So at this point in the neutral axis, the flexure strength is equal 0, okay? So all the time, the stress here equals 0, but the shear is not. Okay, so, and this is the shear diagram, and that's does make sense because we're gonna have a reaction this way, so we will go upward this reaction magnitude here, and then we'll move this way, and this force here will take us down and will move and take us down here. Same here at this point, another force will take us here, go this way, and the reaction will take us up, and this will be the shear diagram, okay? If we had an imaginary section here, and let's say at the distance x, and this is the section, okay? At this section, guys, we will have a shear and we will have a moment, okay? So as I told you all the time, we have a shear and moment, okay? And this is the element status here. If you look at this one, guys, or at this sketch here, so here the shear stress, okay? And because this element is at the neutral axis, there is no flexure stress here. So let's see what is the basic shear stress equation is. If you look at this equation, guys, you will see here, so the stress or the shear stress, and here let's define each parameter. So F here, shear stress is the vertical and horizontal shearing stress at the point of interest. يعني النقطة اللي بدك توجد عندها شو vertical وال horizontal shear, okay? Is equal V, and the V is the vertical shear force, okay? It's a force, and here it's a stress. So at the section under consideration, which is the point of interest, يعني وين أنت أخذت هذا السكشن. Q here, let's leave Q right now. Moment of inertia, which is I, is the moment of inertia about the neutral axis, okay? And it's easy to get this one. especially for rectangular cross-section. And here B is the width of the cross-section at the point of interest. يعني عند النقطة اللي أنت توجد عندها shear كم الويدث للcross section, و this will be a difference, okay? Because if B is small here, you will get the shear stress more, and same relationship with the moment of inertia. Q here, let's get back to Q. Q is the first moment about the neutral axis for or of an area of the cross section between the point of interest and the top or bottom of the cross section. I believe you know that moment of inertia, sometimes they call it second moment of inertia. If you do, let's say y dA here, so that would we call it moment of inertia. Okay, let's see about the x-axis here. First moment of inertia, or this is second moment of inertia. Second moment of inertia, it's y dA. It's not square, and sometimes it's like this, y a. And let me show you a quick example how we calculate Q. I don't want to do that completely, but I want to just refresh your mind. So here, guys, if you want to calculate the first moment of inertia, which is Q here about the x-axis, so it will be here, as I told you, it's going to be for the area between the neutral axis and the top or the bottom of the cross section. And if you do it for this part or for this part, they will be same. يعني ممكن تعمل الجزء العلوي أو الجزء السفلي, you will get the same results, and that's what you can see here. So let's do it for the first, or let's say the upper cross section, and here the area 1, which is this times this. And this is the area 1, and y for the area 1, which is the centroid here, the neutral axis, is equal the whole distance, which is this, minus half of this over 2. So that's what we can do here. Okay, guys. So this, sorry, it's here. Okay, and it's here. This is y1, and for a2, which is this area, you can get it easily, and that's not a big deal here. And if you continue doing this, you will get the first moment of inertia. If you look here, guys, here, just like a summation of y times a, and we have area 1, area 2 times like its centroid, you will get the, which is the first moment here. Similarly, if you do that for the upper part, here's sorry, the lower part, which is this one, you will do same area, let's say 3 and 4 here, and you will get the same value. And as you know, here it's going to be 2 power 3, because we are just multiplying y times a. So this is a basic mechanics of material, and you should be familiar with that, but I just wanted to let's say refresh your mind on this topic. Let's get back to our topic. So let's see in this let's say figure here, we see the shear stress distribution for a wide flange cross section. If you look here, guys, the shear will start here from 0, because as I told you, shear is VQ dividing by IB, and B is here, B is the width of the cross section at the point of interest. So here is going to be 0, and if you start doing here like this shear, here the shear is still 0. Why? Because B is big here. Okay, at this point here, once we start going through the web, B is going to be very small, which is equal T. So here we will have a big shear stress, and we'll keep doing this, and the maximum will be here. This is the maximum value about the neutral axis for this one. So, and as you know, shear stress will be calculated based on this equation anywhere, okay? Because we do have a shear here is, let's say, way bigger for the web. So that means the web will yield completely long before the flange begin to yield. يعني الويب راح يبلش بالييلدينج بالشير طبعا هون will be قبل الفلانج. Okay. طبعا هون this is just an average here. Okay, then I average here for the force. Here, guys, it's a shear force dividing by A. It's kind of what we do. It's similar to what we do in the axial stress. Okay. As I just mentioned, that web will, let's say, yield completely long before the flange begins to yield. For that, yielding of the web will represent one of the shear limit states. Okay, just little bit here. If you see this one, guys, this equation, so this is the V, or the shear stress, which is Vn dividing by the area of the web. Okay, so this one, and all the time, guys, shear stress is almost equal to 60% of the tensile yield stress. So this is the yield stress, tensile yield stress. Okay, we go this way. Let's say this is stress strain diagram. So it's this if this is the yield stress, let's say. So the shear is all the time 60%. يعني 60% من التنسايل yield stress. Actually, it's almost 57%, okay, of this. And the nominal strength for this one, this is the, let's say, stress, and the strength here is going to be this much times this much. Is cross product, يعني ضرب تبادلي. So here is the nominal strength corresponding to this limit, which is 0.6 times yield stress times the area of the web. This is the area of the web. It's here, area of the web. Okay, and the nominal strength of the shear will depends on the let's say width to thickness ratio of the web. If you see it here, okay, it will depend, and this is the width to thickness ratio of the web, which is lambda for the web. Okay, so it will depend on that, and I'll show you what does this mean. So let's see what AISCE specs requirements for shear, the American Institute of Steel Construction, for the shear in the flexure members, which is beam. Okay, for LRFD method, guys, the relationship between the required and the available strength. Required, اللي هو what is the maximum shear in the beam. So if we have a simply supported beam here, loaded, let's say, with a distributed load, what is the maximum shear and where we will use in comparison with or in compare with the available strength, يعني how much the cross section will carry. Okay, هاي الكاباسيتي قديش ممكن الكروس section يحمل، وهذا المطلوب منا. So V sub U here should be less than or equal the design shear strength. اللي هون this is the maximum shear based on the controlling combination of the factor loads. If you remember, we have 7 cases for LFD method. So which one is the max will control, and based on that we will calculate the shear, we will compare it with this much, which is the available strength for the cross section, and this is the resistance factor for the shear, which is phi sub V. Okay, this is for LRFD method. And for ASD method, the applied load, or sorry, the applied shear, which is the maximum shear based on the controlling combination, but here it's based on the, let's say, surface loads, and don't forget this is factor loads, and I think that's very clear for you. And this is the safety factor for the shear. Okay. And these two factors actually, which is phi V plus the safety factor in case of AST method method, they will depend on the lambda for the web. Okay, so these are or these two parameters depends on the width thickness ratio for the web. And don't forget Vn here is the nominal shear strength, and they will equal to each other. Okay, as we did in the previous chapters. So this is the basic shear strength equation, which is here it's equal V sub n is 0.6 times Fy times the area of the web, and we do have a parameter here. These we got it previously. It's the basic one, and this is the area of the web, which is d times the thickness, depth times the thickness of the web, and d here is the overall depth of the beam, يعني كل الدبث للbeam. C sub V, which is very important here, it's the ratio of critical web stress to the shear yield stress. Okay, it's the ratio of the critical web stress to the shear yield stress. And I just want to tell you that from table 3.2 we can get the shear directly, but I have to teach you how to get that through the equations. And if you see here, the value of C sub V is equal or depends on, let's say, whether the limit state if is web yielding or web inelastic buckling or web elastic buckling. So yeah, it's either based on web yielding or web inelastic buckling or web elastic buckling. And let's see the cases for that and check which case is applicable. So for hot rolled I shapes with the lambda here for the web is equal or less than 2.24 under square root EI over Fy. So the limit state here is shear yielding. Okay, so this shear yielding. So the value of C sub V is equal 1, phi is equal 1, the safety factor in case of AST method is equal 1.5. So you're going to use these values and do it, log in them here, and after that you can find strength or design strength based on Al-Kaseasbeh method or AST method. And actually most of the W shapes, when the yield stress is less than or equal 50 KSI, fall into these or into this category. Okay, so yeah, that and this is will be the most used case in this class. Let's move to see other cases. So this is case number 2 here. For all other doubly and singly symmetric shapes other than I shape here, the phi is equal 0.9 and the safety factor of AST method is equal 1.67, and CV is determined as follow. If the width thickness ratio of the web, which is h dividing by the thickness of the web, is less than or equal 1.10 under square root k sub VE dividing by Fy, so there is no web instability here. So C sub V is equal 1, okay? And if the lambda or width to thickness ratio of the web is greater than this much, which is 1.1 under square root k sub VEI over Fy, and less than or equal this much, which is 1.37 under square root of this much k sub VEE dividing by Fy, so we do have inelastic web buckling here, and C sub V can be calculated using this equation. Okay, just let me get the whole thing shown here. So it's going to be using this equation here, For if the lambda or width to thickness ratio of the web is greater than this much, which is 1.37, the square root of this, which is kV times E dividing by Fy, the limit state is elastic with buckling, and C sub V is equal, is calculated like this. And here is guy like K sub V is equal 5, and this is for unstiffened web with lambda is less than 20 or 260. There is no value if we do have lambda is greater than 260. And I'll show you this in, let's say, a sketch, which will make it much easier for you guys. As I mentioned to you guys, so Vn is equal 0.6 Fy times the web area times C sub V. So here, if you look at this, let's say a sketch here, so this is Vn, okay, which is here, as a function of lambda, which is h over the web thickness here. So, as I told you, if web thickness is less than or equal this much, which is 1.1 and the square root of this, so we will have C sub V is equal 1, guys. Okay, so here 0.6 Fya, let's say the web area. So here we're gonna have C sub V is equal 1, so it's multiplied 1, so that's completely fine. But if we do have it here between, let's say, this limit here, which is 1.1 this much and the square root, less than or equal 1.37 and times this much under the square root, we will have it 0.6 times Fya, or the web area, times CV, and CV here, which is C sub V, is equal this much, okay, as I showed you just in 1 minute ago. And if it's greater than this much here, okay, but we do have a maximum limit here 260, as I mentioned to you, for unstiffened shapes. So same here times C sub V. يعني يا شباب معنى الكلام إنه هاي المعادلة هون هاي ثابتة هون، بس بكل حالة عندنا قيمة سي في. هون سي في is equal 1. هون is equal this much. هون بالليمت طبعا هذا، احنا نحكي عن الليمت هذا أول شيء هيو. الليمت هذا هون this much. طبعا احنا maximum limit عندنا 260. this shape or this sketch يعني زي اختصر لنا كل هاي الحالات. Okay, for let's say allowable stress formulation, which is AST method, guys, here. Okay, so it can be written in let's say let's say the applied shear, it should be less than or equal Vn dividing by the safety factor, and I think I showed you this formula. Okay. And sometimes it might be written in, let's say, in terms of stress, because V here, or F sub V, F small طبعا, it's V, يعني let's say dividing by each side by web area. يعني قسمنا الطرفين على web area راح يصيروا stress. فبهاي الحالة is going to be stress, which is this much, the applied shear stress. And Vn is here, it's this one, Vn dividing by safety factor dividing by area to be a stress. Vn here, this much is 0.6 times Fy times area W, which is web, times C sub V, هاي أخذناها قبل شوي, dividing by area, which is here, dividing by stiffness factor, oh sorry, the safety factor, which is here. This is allowable shear stress. Allowable shear stress, it should be greater than this much, the applied shear stress. And applied should be less than or at least equal the allowable shear stress. And we're going to use the same cases, but for case number 1, and this is for the most hot-rolled eye shapes, C sub B is equal 1, as I told you, and the safety factor is equal 1.5, okay? And this is going to be 0.4. Don't care about this, just use this as it is here, and the cases as we did mention. Here the same note was mentioned to you in the shear is all the time, is rarely happen for the hot rolled steel beams. And so you have to design the beam for flexure and then check it for shear, and later you need to check it for, let's say, deflection. Let's solve example 5.7, page 220, and see how we're gonna use these formulas and cases to check the shear for, let's say, a design flexure beam. So this is example 7, sorry, it's 5.7, page 20, let's say 220. So in this example, we need to check the beam in example 5.6 for shear. If you remember, in example 5.6, that was page 212, we have a simply supported beam, okay, and was 45 feet in the span length, and was loaded with shear, dead load and live load, okay. And the cross section was for this اللي هو wide flange 14 by 90. So in this case, we need to check this for, let's say, shear. The basic equation for the shear here, Vn is equal 0.6 Fy times web area times Cp. Okay, so right now, area web, it's easy to get area web, which is this much here. It's d, the depth of the beam, times tw, which is the width of the, or sorry, the thickness of the web. So the web here, or the depth is 14, and the web thickness is 0.44. So this is the area, which is 6.16. From where you can get this or these values? From part 1 in the steel manual, and I'll show you how we gonna get that, because we need to get the lambda for the web to check which case is applicable for this beam. So let's go just briefly to the steel manual and see you from where we can get these info. Okay, in part 1 of the steel manual, this is wide flange 14 by 90, and if you see this is F superscript, it does mean that this section is non-compact. And here is the depth of the section. Just let me take it down and show you the title here. So yeah, this is the depth, which is 14, and sometimes it might be not exactly 14 for some cases. Look at this, it's 14, but actually it's 14.3. So you have to check it from here. So 14, and the web thickness is 0.44. So this times this is the web area. And if we go to the next page, guys, look at this one here. Okay, this is the next page here, and the lambda for the web is equal 25.9. Okay, so this one, memorize this value, and let's get back to our example. So here is the value that we got it from the manual for this cross section, which is wide flange 14 by 90. And if we go down, guys, okay, and this is the area of the web, 14 times this again. And let's check the cases right now. Which case is applicable for this beam, and how much C sub V here, and phi for shear, and the safety factor, how much. So in this case, we're gonna compare this, which is the lambda here, each dividing by the web of the, or thickness, web thickness, with this limit first. So 2.24 under this, so it's 54, and the lambda is less than this much. So the strength is governed by shear yielding, and C sub V is equal 1, okay? And the safety factor actually is equal, let's say 1 for the RFD method and equal 1.5 for ASD method. So here, guys, right now we are ready to calculate the nominal shear strength, which is Vn 0.6. Fy, it's given to us 50, and web area we calculated from here, and C sub V we did decide to take it 1 based on this condition which is met here. So the shear is equal 184.8 kips. So this section can carry this much of shear. Right now we need to find let's say the LRFD method strength and the ASD method strength. Let's go down just here. Okay, for LRFD method here, as I told you, based on this condition, phi sub v is equal 1, so it's going to be 1 times the value we just got it, so it's approximately 185 kips. So right now we need to compare it with the maximum shear under or for LRFD method. So here, if you remember from example 5.6, the factored load or distributed load was this much. If you go back to this example, you will see how we do it. So, and L is equal 45, and this is simply supported beam, guys, okay? Simply supported beams loaded with the distributed load اللي هو هون WU, which is the factored one here. So as you know, here will be the maximum shear, and this one is going to be distributed load times L dividing by 2, distributed load times L divided by 2. This is the reactions, okay? هاي لأنها هاي كلها distributed load intensity times L dividing by 2 dividing by 2. So calculating this one here, this is the applied shear or the maximum shear we can get. So this value here is 46.8 kips, which way less than the capacity of this beam. So this beam is okay based on RFD method. And if we do that for ASD method, guys, just like this, for ASD method, Vn dividing by safety factor for V. So Vn is, which is 184.8, or as they took it here, it's 105 dividing by 1.5, and 1.5 that based on this condition, okay? Don't forget this. So this much is equal 123 kip. Okay, so compare that and see what is the maximum shear. If you remember for ASD method, which is the surface load, the load intensity was equal 1.4 kip per foot. And you can check it back from this example again. So using the same formula here, because this is, some depends on the ASD method or LRD method. So we will get the maximum shear is equal, or let's say the applied, is 1.4 times 45 dividing by 2, and this is equal 31.5 kip, and which is way less than this value here, which is 123. يعني الشير المطبق بكلا الحالتين أقل بكثير من الكاباسيتي لهاي البيم. So the beam is okay, and I think, yeah, it's here for the ASD method. Same thing, you will see it here, and yeah, same here. Okay, it's similarly shown here. And for, if you go to table 3.2, guys, you will see that you can get these values directly from there. Let me show you that in a short moment. So in this table, which is 3.2. This is our, let's say, cross section, wide flange 14/9. So if you go here, these guys, guys, look at this one. This is the shear for ASD method dividing by the safety factor, and here it's ASD method in kips, and here is for LRFD method in blue. So if you look here, it's 123 as we got it, and here it's 185 as we got it, and just compare these values with the maximum shears and you will get them directly. So you don't need to do the whole calcs that we did unless I ask you to do. So by this, guys, we're done with this example, and please, if you have any questions, send me a chat or an email. ويعطيكم العافية.